have our first CAM speaker to be one of our own, who I don't think needs an introduction, but Abhishek Balakrishna will talk to us on end behavior for a flutter model. Thank you, Abhishek.
Thank you, Sue. Good afternoon. So today I'll be talking about the end behavior of a particular fluid and structure interaction model. And as the title suggests, the particular end behavior that we're sort of interested in is that of flutter. So there's a very technical definition of flutter that's given there, but we'll break it down as we go along. So it says that it's a systemic instability in a flow structure occurring when the natural modes are destabilized by aerodynamic loading. So anyway, quite a technical definition. We'll break it down as we go along. Fortunately for us, the scientists at NASA in the 60s have made a fun video regarding flutter, which I'll just show you. And you'll see this showing up in the video. It's a Tacoma bridge that collapsed. I'll just show a small portion of it. Flutter in action.
So dancing is a form of flutter.
Yeah, you can say that. So as you can see, this that's essentially a few examples of flutter. See, and this another case where flutter could be quite dangerous. So I just wanted to sort of focus on this missile. So engineers have been interested in this problem for quite some time. So apart from this complicated definition, essentially it's some flow-induced instability of flexible structures that we sort of see. And seeing oscillations in the structure, we might be tempted to sort of model it as a traditional resonance. But it turns out that it's actually quite different from traditional resonance, as in we don't really require periodic forcing to induce this sort of flutter. It is in fact caused by bifurcation in the parameters of the problem as it reaches some critical value. There's some instabilities, and that's what it sort of leads to.
Wouldn't that critical value be the resonance, the oscillations of the linear part?
Yes. So like I said, so the onset of flutter is actually decided. The linear part of the problem decides the onset.
Okay.
And once there is onset, to sort of qualitatively describe what kind of fluctuations we see, we need to model in nonlinearity into the problem. And to sort of see these points in action, we'll just sort of take a look at this toy model that engineers have sort of come up with. So here we see a one-dimensional rod that's clamped at both ends. And the vertical, W here represents the vertical displacement of this rod. And above this rod, we have fluid flowing horizontally with the constant velocity of magnitude capital U in the x direction. So here we have the model. So we have a damping term. We have this non-local nonlinearity. And then the right-hand side, the term we see terms that appear because of the fluid flow flowing on top of the structure. we have clamped boundary conditions, and we provide it with an initial condition. And we'll sort of put together the behavior of this model piece by piece, right? So first let's say, okay, we don't have the damping, we don't have nonlinearity, we don't have flow, right? Just in vacuum, what does the system do? If I plug in these initial conditions, I'll just see oscillations. Now, if I, and they don't die out, right? No damping. So now when I introduce damping, we would sort of see what we expect, which is that the oscillations sort of start and slowly die out. Okay. Markable there. Now let's introduce flow. Now, when we introduce flow, and this is where sort of the bifurcation part of the problem sort of comes in. So there's a critical value flow beyond which we expect the bifurcation to occur, and then we see flutter. So in the subcritical flow, what do we see? So here we have flow, as you can see, it's affecting the movement of the plate, but still the damping is sort of able to dominate and just kill the oscillations. And now we sort of see what happens when we sort of increase the flow beyond the critical value. And now we see sort of the onset of flutter kicking in. But since we have not introduced nonlinearity, the amplitude sort of keeps going up. And now, lastly, the last piece of the problem is introduced, which is nonlinearity. And when the nonlinearity kicks in, we see that it just keeps the oscillations bounded. Yeah.
Now, when you introduce the flow, do we see it as a force acting on W, or is that becomes a system of feedback couple?
Yeah, it's a couple system. Yeah. So yeah, I'll introduce the model specifically that we look into, and it's a couple. So here we sort of see the complicated definition we saw sort of in action, that the system had some natural modes, and then the flow, when the flow is introduced and it reaches a critical value, it destabilizes this mode, and we have flutter. And then the nonlinearity keeps the oscillations in check. So when engineers and mathematicians started looking into this, they wanted to model this, right? So what kind of questions and answers are we interested in? Right, so the first 4 points here are essentially about modeling, right? So you want to come up with a good PD model with good notions of solutions, and then decide on what kind of initial and boundary conditions we want to sort of come up with for the model fluttered. And once we have the model, once we have established the model, we want to see, hey, can we control? Like, when do we not see a flutter as an end behavior, like non-transient behaviors? When do we see flutter? And can we and flutter is sort of seen as a long-term behavior, right? We wait and then we see eventually, well, how does the system behave? So can we reduce the set of essential dynamics to a small set, right? That's also a question that we are interested in. So the model that we'll be looking at is this sort of described here. So we have the 3D half space, and in the XY plane, we have this region omega, which is sort of the elastic part. And it's clamped on the boundaries. And then above this, we have fluid flow. The fluid's flowing horizontally with the velocity of u on top of it. And u is sort of normalized in a way that u equal to 1 represents Mach, which is the Mach 1, which is the speed of sound. And here's sort of the model. So u represents, little u represents the transverse displacement of the plate, which we're trying to model. V here is the velocity potential. So more precisely, we have stationary horizontal flow above the plate. And then as the plate develops, it perturbs the velocity of the flow above it. And phi represents the velocity potential of this perturbation of the velocity about stationary flow u. And we have the model here. Here's the plate, the equations for the plate, where we have damping. We have a non-local nonlinearity here. P naught is some static pressure that the plate might experience. And this is the term coming from flow.
Where did you get this model?
So this model was sort of proposed by Earl Dow. Oh my God. Hopefully that works. Okay, yeah. Sorry, just updating. So Earl Dowell was sort of what who sort of proposed this. And for the flow, we have phi, which is these equations for phi. Here we have the potential flow model. And it almost looks like the wave equation from U showing up here. And then on the boundary, we have the velocity matching condition, which is that the vertical velocity of the fluid matches the vertical velocity of the plate. And we supply it with initial conditions. And the potential flow model is sort of obtained by linearizing the compressible non-disturbs about this horizontal flow, U in the x1 direction. Okay, so this model has been looked into for quite some time, and there have been two main sort of ways of attacking the problem. So the first, the more traditional way is that you sort of find ways to decouple the plate and the fluid equations, solve one and feed the solution back into the other. And we'll be talking more about that method in this talk, because when we do that, we run into some issues. And I'll talk a bit more about that, but that will be the main focus of our talk. There have been newer methods by Webster, Troishaw, and Dr. Leszewska, where they were able to sort of they did not decouple the system because they said, okay, we run into some issues here. And they treat the whole system as one big piece, and they sort of come up and through a lot of semi-group machinery, they're able to sort of show existence of solutions. And it's called a cancellation-based method because the problematic terms that show up when you decouple the system sort of cancel each other out when you don't decouple them and treat them as one big system. So they were able to show existence of solutions, well-poserness for these systems. For both these cases, U less than 1, which is in the subsonic case, and U greater than 1, where the speed of the fluid is greater than the speed of sound. In the subsonic case, you're able to show that the solutions are bounded in the natural energy norm for the spaces. But for U greater than 1, you're not able to keep the solutions bounded. And this will, this is something we'll see later on too, that engineers have sort of observed that you don't really see flutter or things like that in subsonic flow. And we'll sort of see why that is more. Yeah.
So why U equals 1 is a challenge?
Yeah, so one way we can sort of see this is looking at this flow equation. So if you just try to sort of find the energy, right, multiply by phi. On the right-hand side, because of this Laplacian, when you multiply phi, integrate by parts, you're going to get a term partial x phi squared, right? On the left-hand side, because of this partial x phi showing up here, again, when you multiply and integrate by parts, you're going to get U partial x phi squared. So when you bring the two together, if U is greater than 1, then the sign of partial x changes. And that's why then the energy is sort of not bounded and you run into trouble. That's why the U equal to 1 is sort of that borderline case. Okay, so yeah, so using these new methods, they were able to show that if the flow is subsonic and there's some kind of damping in the structure, then eventually you won't see any kind of dynamic end behavior. They were able to show that things die out. They go to a set called the stationary set, which I'll talk about.
Does U changes with respect to X and Y?
No, U is
it's
a constant.
It's constant.
Yeah, for the purpose of this model, yeah.
And U is defining your subsonic or supersonic
flow. Exactly.
It's called by U.
Yes, exactly. Yeah.
And the motion of the plate just slightly perturbs
U,
exactly. And that so that the fluid equations are linearized, right?
Yeah.
And that linear system for the fluid is described by the potential phi.
Yeah, exactly. Yeah. And but when we try to sort of do the same, to attack the same problem by just decoupling the two systems, we run into issues. And I'll talk a little bit more about how we go about decoupling them and what issues we sort of run into. So for the flow equation, we have these set of equations, and since they're linear, by superposition, we can split them up into two sub-problems involving phi star and phi double star. So for phi star, we say, okay, we have zero boundary conditions, but we have the respective initial conditions. But for phi double star, we have zero initial conditions, but we have supplied them with appropriate boundary conditions. So here in the first equation, in terms of long-term behavior, we can sort of ignore them. And the reason is Huygens principle. So what Huygens principle essentially says is that suppose, as an example, so suppose I restrict my attention to this room and I create, let's say in the fluid in this room, I create a localized disturbance. Let's say I clap. Then the disturbance is localized around my hand. It spreads. And as time passes, you hear the clap. It passes you, and then the people behind hear the clap. But if I wait long enough and I restrict my attention to this room, the effect of the clap completely disappears after a certain point in time. And so essentially, if my initial conditions here, phi naught and phi 1, are localized to, let's say their support are localized to a compact set K with diameter rho, and if I restrict my attention there and wait long enough, then it's got the effect of the flow is just going to completely go. The effect of the initial conditions is completely going to go away, and then they just become zero after a certain point in time. Whereas here, for phi double star, we can explicitly solve this problem. And in an expression for phi, in terms of u. Now, this expression is a bit long, but the main takeaway from this is that we can write phi double star in terms of ut and ux diagonal. And the expression for f diagonal is this complicated expression here. But the main takeaway is that I can write phi explicitly in terms of u in that case, because there was no initial conditions coming from phi, and any kind of disturbance in the fluid is coming from the plate after a certain point in time. So now this helps us decouple plate equations from the flow, because now we could write the flow terms that showed up in the plate equation in terms of u, again, using the formula that we have here. And then we sort of decouple the plate equation from the flow. And this is the system that we obtain. Now, in the new system, the terms on the left-hand side are exactly the same as we had in the original system. P naught, again, we had them. And we just have these two new terms showing up. Nothing very special about the first term, but the second term is actually quite interesting. So the second term, again, is defined by this huge integral here. But essentially, what does it say? It says that, hey, to define my Q, I need to know U at time t and going all the way back to t minus t star. So essentially, behavior of U in the past affects the behavior of U at present. And we should expect this because let's say there's fluid flowing above the plate. As soon as the fluid particle reaches, is above the plate, the motion of the plate affects the fluid. And then this change is carried forward, and then the changed fluid affects the plate. And this happens, so that's why the behavior in the past affects the present, but for how long, right? So as soon as there's change in the fluid, and this changed fluid has completely passed over the plate, now that change no longer affects the plate. So that time t star, which is basically dependent upon how fast is the fluid going, which is u, and also how big is my domain. And that's essentially what that term is. And that's why this is called delayed dynamical system, because there's a delay between cause and effect. And it turns out that this system has a compact global attractor. And now moving forward, the idea would be that, hey, there's some stability that I'm seeing in the plate. Can I transfer that stability to the flow using that flow, using the connection between flow and the plate? And that's where I'll run into issues. So, but before that, I'll just mention, like I promised, what stationary solutions for the problem are, which are essentially, they solve the same exact equation with time derivatives being equal to 0. And we represent the set of stationary solutions by n. So here's where Earl Dowell sort of comes in, and he's an engineer, and he's been looking at this problem, and he's done some wind tunnel tests, and you saw NASA have been sort of working with this as well. And what they sort of observe is that, hey, when we have the subsonic parallel flutter is very unusual in aerospace. If the trailing and the leading edges are fixed, which is what we have in the form of a clamped boundary condition, we see divergence rather than flutter. And divergence is just some static instability. So it just buckles or something like that. There's no dynamic end behavior that we see. So there's this conjecture that, if we have subsonic flow, then eventually U and phi would approach the set of stationary solutions. That's what this essentially says. U would approach the set of stationary solutions, so does phi, and ut and phi t will go to 0. Now, how can you sort of see this from the model? Right? Why should this be true? And so here, the essential sort of outline of the map was this. So we have the energy that's bounded. And then E of t and E of 0, all these quantities are positive. So we say, okay, the integral of ut must be bounded. Now, we can leverage this fact along and use the existence of compact global attractor for the plate system to sort of conclude that ut will go to 0 in L2. And you can find a sequence of times Tn going to infinity such that ut will converge to a point in the global attractor. Okay, so we have some stability in the plate now. Now, we want to transfer this to the flow using the flow plate formula, and that's where we run into issues, especially with the phi t term. And the main issue that we sort of run into is a loss of regularity. And I'll talk a bit more about this loss, but then we're not done yet. So once we show, let's say we are able to get through this. Yeah, sorry.
When you say global compact attractor, in what topology?
Oh, in the original energy space, we can show it has higher regularity as well, but essentially, so H, yeah, in this space. So it's essentially for phi, it's an H1, and phi t is in L2, U is in H2, and ut is in L2. That's sort of what we are working with. And once we show, okay, then if you're able to sort of get through this critical step, we get that U will converge to some U hat in the global attractor, phi will converge to some phi hat. And the last step is to sort of show that U hat and phi hat are in fact stationary solutions. So no dynamic end behavior, and we will have a result. So in the past, when mathematicians were sort of working with this flutter model, and they employed this decoupling method, they employed it in a slightly regularized version of the problem. So instead of having just UTT or just the damping UT, they had M alpha UTT and M alpha UT, where M alpha was the identity minus the alpha times Laplacian. So that added a bit of regularity to my problem. UT, instead of being in L2, is now in H1, and that sort of helped us. And we'll see why. And they were able to show this result that we are trying to show for my original model. And the reason is sort of described in the slide. So if you're looking at the flow, potential flow model with appropriate boundary data H, then if your H is in H half, then you can lift the boundary data to the flow in the appropriate space that we need, which is we need phi to be in H1. But if it's just L2, then Tataru has shown in his work that best you can do is H2 thirds for phi and H minus 1/3 for phi t. And that's essentially the difference between the two problems. So the boundary data in the regularized version, U is in H2, so UX is in H1, UT is in H1, the whole thing's in H1. It passes, it's greater than H half, and we are able to sort of decouple, lift, and do business as usual. But now because my UT is in H, no regularization, it's in L2, we run into issues. We don't have enough regularity to lift this boundary data. And this is where we were sort of stuck at some point. Before I sort of say how we sort of ended up solving this problem, I'll just mention a little bit of microlocal analysis which came to our aid. So the idea here is that you take the, let's say, the Laplace transform in time, Fourier transform in space variables, and you go to this Fourier Laplace space. You now in the space chop the space into smaller pieces, let's say, and then analyze your solution in each of these pieces. And that could give you some additional information about our solution. And for our case, we're going to do something similar. So we have, let's say, the time, you take the Laplace transform in time and you have this, and then you take the Fourier transform in space to get eta. So now you just take this Fourier Laplace space, you divide it into 3 parts. So let's say the first part here is where sigma dominates eta. And in that region is called the hyperbolic region. And then you have the bottom part here where eta dominates sigma. It's called the elliptic region. So here, time dominates space, space dominates time. And in the middle, eta and sigma are sort of comparable. And a sort of motivation to sort of divide it into these 3 pieces, that in the middle area, because we're in this Fourier Laplace space, multiplication by the symbol is like a differentiation. So in that region, since the space and the time variables are comparable, multiplication by differentiation in space and time become comparable then. They're interchangeable. And that's sort of the idea, because UX is H1, whereas UT is L2 for us. So maybe this could help us. And also we analyze, let's say, phi t in this microlocal space. So we say, okay, let's say we have L2 data, and we're trying to lift this and obtain phi and then phi t. We want phi t to be in L2, right? So we see that in the hyperbolic and in the elliptic regions, we do get phi t in L2. But in the characteristic region, based on our crude calculations, we see that it's just H minus half. So the main loss in regularity that happens while lifting our data occurs in this characteristic region, right? So now we're able to sort of pinpoint the problem, which is the loss in regularity. And we're also, through this microlocal analysis, see that it's in this characteristic region that we experience this loss. And before we even knew about microlocal analysis, we were sort of just looking at this problem and seeing what can we do. And to come up with a formula for phi t. So now phi, like we saw, we can define explicitly in terms of the plate, u and ut. So when we try to just differentiate that with respect to time and obtain phi t, we get certain terms on the right-hand side involving utt. And we want to move away from utt and come, maybe at best go to ut. So we use this formula because everything here is in terms of the dagger. So here, partial t of h dagger for some function h can be written in terms of this equality. And we observe that the left-hand side has time derivatives, whereas the right-hand side does not. We have derivatives in terms of the other variables. So initially we thought, hey, why don't we use this again to change ut and write it in terms of spatial variables, and maybe that'll help us. And we communicated this idea to Dr. Leszewska, who has worked on this problem before. And when she heard us say, oh, we're thinking of changing space derivatives to time, she thought microlocally. And so we had this miscommunication, but in fact, that helped us out because I did not know about microlocal analysis at that point in time. And I tried this. And this, we are not able to completely do what we want with this idea. We again hit a wall. But then because of this miscommunication, microlocal analysis came into our radar, and we sort of looked into the problem through this angle. And that really helped us because in the characteristic region, we can change time derivative to space, and we have H1. And that's precisely where the loss happens of about a half. So with this idea, we were able to sort of implement what we wanted to do. And I'll just briefly mention what we sort of did. We just, with a change of variable, we were able, for the flow equation, we get this equation right here. And then in the Fourier Laplace space, we were able to sort of obtain this bound for eta and eta t in the interior and in the boundary. And we were able to bound that in terms of this norm in the microlocal space, X. This essentially, it's a weird space, but essentially what it does is that it applies the H half norm in the characteristic region and takes the L2 norm in the elliptic and the hyperbolic regions. And our function, the boundary data, is in fact in that space because it has additional regularity in the characteristic and just L2 regularity in the elliptic and hyperbolic. So we were able to sort of obtain this inequality, and then we were able to bound the microlocal space norm in terms of our usual Sobolev norms. And now, through these inequalities, we can transfer the stability on the plate to the flow. And this sort of worked. And we were able to sort of put to rest this 30-year-old open problem, which by essentially just saying that, hey, we can decouple the system. The only issue was that we just had to analyze it microlocally to see that we, in fact, don't really have any loss of regularity. And we were able to show that in subsonic flow, you won't see any kind of flutter. And yeah, it sort of ends my talk and no other references. I went by pretty fast.
Well, it's better than going over time. So.
Yeah, sorry.
2 questions.
Sure.
So when doing microlocal analysis, you mentioned Laplace.
Yeah.
How do you invert it after you do your analysis? How do you go back to the original space? Because it's not as easy as...
Yeah, it's not as easy. So initially, we just work with the microlocal norms. And then we just want to go back. The formula is a bit, so...
I mean, I know that there are several different formulas based on several different assumptions.
No,
is that
it's a bit straightforward to go back and forth. So here you would just multiply by the space. So these two spaces you have L2 norms. Let me just think. Yeah, exactly. So you have some bounds on. So here this is between maybe sigma equal to root 2, 1 over root 2, and things like that. So you use a little bit of that. You can't exactly come back. What you can do is you have norms, and then you can bound the norms in terms of the Sobolev spaces based on the integrals that you have. We don't exactly invert the functions themselves. We work with the norms, like I said. There's a bound in terms of microlocal space, and the microlocal norm can be bounded in terms of the Sobolev norm, and that's enough for us. The microlocal is just an intermediate step.
Second question.
Yeah, sure, yeah.
So in the case of parabolic equations, there can be some pathological cases where time derivative decays, but you don't converge to the solution of the stationary problem.
Yeah, you can. So here, you can, because the plate had a compact global attractor, we wrote the flow in terms of the plate. And then we were able to show and sort of transfer the stability of the plate. We didn't directly work with just the hyperbolic, like it's coupled to the plate. So that helps us. So the plate has a global attractor. And then we write phi purely in terms of U. And then we use the fact that U has a global attractor to show that phi would also converge to a stationary solution of the problem.
How rich is the global attractor? Because you don't have any forcing term to generate like a rich dynamics, a complicated attractor. Is it just the stationary points and maybe some curves connecting them?
Yeah, I don't really know. It's actually it's actually a tough problem. But
do you have like any lower dimension on this attractor, like any unstable manifold there that you can?
Let me see.
There is nothing that in the equations, there is
Yeah.
nothing that gives you the possibility of having a very complicated attractor.
Yeah. Yeah, at least in the subsonic case, I don't see something crazy happening.
Well, the fact that you have a rather simple attractor, it would appear, does that partially explain the implication that there will be no flutter in this situation?
Yes, subsonically, yes. Yeah, because again, I don't, there could be other stuff in the attractor showing up, but at least for our solutions will converge to stationary solutions. Like the set of stationary solutions, it gets closer and closer and closer.
How rich is the set of stationary solutions? Like how many stationary solutions do you have?
Oh, yeah. Again, I think the answer is we don't know. Not just I don't know, I think we don't know. It could
But
be.
you know it's not empty, right?
Yeah, it's not empty. Yes. Yeah.
How do you know that it's not empty?
There will be some trivial state.
Yeah.
Is there a trivial stationary state?
Thinking about that.
I mean, it's like, it doesn't have forcing terms, so zero would do.
Yes, zero will be.
I think at least for the flow, yes. And
Okay, but if it's really zero, then you wonder whether there is something else but zero.
yeah, I think I'll just have to think and come up with it. But there must be apart from zero as well.
No, the Navier-Stokes equations, we don't know if there is something else but zero. I mean, in some cases, you can prove instabilities and then you can find some. But otherwise, there is an attractor and it's really something we don't know, but it may be just one stationary point.
Yeah. I'm a bit more hopeful because of no forcing. Yeah, okay.
And then if you have nonlinearities, can you do this this decomposition of the modes?
Yeah, so you can, this is just to sort of see what space it lies in. So yeah, you can still do it. Yeah. Yeah, because essentially the idea is
it works when you have that f of u that you have like in that model.
Yeah. So this is essentially just to check the norms, essentially. So if you, so here the idea, the idea is like, if I want to take a derivative in this at any part here, if I multiply by, let's say, eta to the power half, I can change this to sigma as well. And that gave us an advantage. So you can still analyze it in different pieces, depending on what you can. Some people even do it differently. If they have trouble in this region, they say, we'll treat this separately. And you can analyze the function in the regions in any case. Yeah. I think maybe I talked a bit fast when I was in house. Yeah, just really.
Well, it's a good practice.
Yeah, when I practiced at home, it took me about 45, 46 minutes. So and now it's just like 30 minutes.
We asked questions, so.
Yeah. It's 40 minutes I was done here. Yeah.
So what's next then?
Oh, maybe, yeah. So supersonic is still a little, because the energy is not bounded. It's long-term behavior is still an issue there. And we
but then you probably are expecting flutter.
Yes, exactly. But can you sort of tell me when it's not going to be chaotic and just break, or can you say when you have these oscillations that are bounded?
Can you take a piecewise constant u, where at some places you make it equal 1, and somewhere else you make it less than 1. So you are not, you can reach like supersonic, but you're at u at the level.
Oh, yeah, that'll be a bit of a different model. So because it's a flow, you want to make u. Okay.
So I would like u to be less than or equal to 1, but it reaches 1 sometimes.
Okay. Okay. Yeah, I think transonic, which is like very close to one, and then supersonic, yeah, these are still areas you can work on. But maybe you probably won't be able to say something like no flutter because flutter does happen in supersonic cases. But maybe just qualitatively you can give a better idea of when can you have control flutter, when can you have chaos, and things like that. It should be hard, yeah.
Any other questions or comments? It's thank.
Seems like there's another page.
Oh,
Yes, we didn't see the last page. Thank you.
Thank you.
yeah.
I would say it's slightly notationally confusing to be calling capital U and little u all the time. And of course, when you're looking at it on the board, you see capital U, but when you're speaking about it, those two U's become a bit confused. Yeah. Maybe it would be better to call it capital V.
I should do that. Yes. Yeah.
But traditionally, obviously, many people have worked on this problem, so probably don't worry about the confusion of capital U and little u.
Yeah, and writing is pretty clear, right?
Yes, but in speaking,
yes. Yeah.